Hello class, it's Mr. Samingo. Sorry I couldn't be there today, and sorry for the last minute notice, but you might hate me for this, but this particular section is very difficult. We're going into the problems. What we're probably going to focus on the rest of the semester is these word problems that you guys hate for the AP exam, but we'll practice enough or make you feel confident enough that you guys can solve these. So I'm not going to lie, they're not very easy, but hopefully if you see it enough, or maybe because of my expert teaching, you guys understand it a little bit better. So this one is called optimization, and you should have seen it last year. What you're trying to do is you're trying to, again, this whole chapter is about how do you use derivative in real life. So we did mean value theorem, Rolle's theorem, graphs, all these increasing, decreasing, concavity, stuff like that. But this one's a very engineering type problem. So let me give you an example before you even start with the notes. The first example is, let's just say like I have a piece of paper. And I want to make a box with this paper, and with this paper I will cut squares out of the corners. So here I am ripping some squares off the corners. And let's just say I want all these squares to be the same. And I'm not like the best paper ripper in the world, so these aren't perfect squares, but close enough. Sorry, my iPad turned off, but hopefully you're following me. So look, cut out squares from all the corners. Okay. Now what I'm going to do, since I cut out all these squares, what I'm going to do is I'm going to fold up every side. So if you want to see, I'm taking each. Sorry. I'm taking each of these. I'm going to fold each side like so. So I'm folding each one. And if you want, I mean, you could try this, not like the exact same time, but you could try this at home. And now you see I have a kind of a box, right? And the question is, and what calculus can solve and what they use calculus for in real life is, what is the size squares in the corners? Like, what do I have to cut if they all have to be squares that gives me the biggest volume in this box? Or I want to store the most water in this box. What can I do? And this is a real problem. So when you buy cardboard boxes, or people buying boxes in bulk, companies are like, no, seriously, like, what do I do? Same thing with water bottles. You guys have seen like many different water bottle brands that have all different designs. Like this one is the Costco brand. It has this like curvature and these little ridges. Arrowhead has its own. Like all of them are trying, essentially, they're not trying to be, I mean, they are trying to be eco-friendly, but they're trying to use the least amount of plastic so they have to spend so much. What can calculus do to help us make that easier? So we're going to look at this first problem in your notes, and it's actually a very similar problem to what I just did for you. So here are the steps. With anything with math, as I've told you like many times, like it's so much easier to remember the steps like once you do some sample problems. And some of these I'm going to cross out. So first one says assign variables in the problem. So I'm going to simplify this and just say, let's just draw a diagram. Okay. And then I'm going to skip over number 2. First of all, you're going to draw a diagram. And let's cross out number 2. Okay. Number 3 says you're going to determine the variables maximum and minimum. So like the very first thing I want you to do after you draw a picture is identify what are we trying to maximize or minimize. So if I need to, or how about this, I'll use a highlighter. What's that variable that you're maximizing or minimizing? Okay. If necessary, you're going to use substitution, or another way to think about this is that I need to get the equation just in one variable. Okay, we're going to skip over this interval that makes sense, and then we're going to find the absolute maximum and minimum, or minimum. So it's really a 3-step process, or draw a picture and then a 3-step process. Again, it won't make sense until you actually do this. So again, as you noticed, this first example looks exactly like what I just did. You have a sheet of paper, 11.5 by 11, and you want to make an open box by cutting up squares on the sides. The question is, what size squares should I cut so I get the largest volume in this box, so I could store the most stuff in this box? So again, step 1, what you're always going to do is draw a picture. I'm going to draw like a top-down picture, like so. So here's my 8.5 by 11 paper, And I'm going to cut out squares from the side, so let me draw me cutting out these squares. Now, what I crossed out, but what you're going to do now is you're going to need to assign variables. Now, when you assign variables, obviously you can assign variables to everything, but you want to use as little variables as possible. Like you don't want to have like x and y and z, and you want to get like 1 or 2 variables at the most. This one, since they're all squares, I want to know how big to cut them. So I'm going to call these all x's. So since they're squares, they're all x's. Another thing I could also figure out is, well, that's all we're going to do for now. Drew a picture, put variables, and I'm done. Step 1, and I'm not even going to look at the question because I sort of already know what I'm looking for, or we read it already. It says like, what do I cut to make it the largest possible volume? So again, I told you step 1 is read the question and find out what are you trying to maximize. So in this problem, I noticed that what I'm trying to maximize is largest possible volume. So what you're going to do in step 1 is you're going to write the equation for volume. Okay? So volume of a box, if you remember, is length times width times height. That's the volume of a box. Okay? Now, what you're going to do next is, you notice I have 3 different variables. Okay? So again, step 1, find out what you're maximizing, write out the equation for it. The next thing you're going to do is you need to figure out how to, we're going to maximize this equation right here. This volume, length times width times height. We're going to maximize it, but I need to put it in one variable. I can't maximize them. I can't take the derivative of 3 different variables. I need to put them all in the same variable. Well, I have these x's and I have these length times width times height. Let's see if I can do this. Okay. Length, if you may notice, let's just say this is length. Like I have this x, this x. There's one piece of information that they gave us that you might have noticed. They said this paper is 11 by 8.5 inches. Okay. So what I'm going to do is I'm going to say this length right here, in an 8.5 by 11 paper, this is 8.5 and this is 11. Here, let me write it out for you. This is 11, this is 8.5. Now, when I cut these squares, right, when I cut the squares out of this thing, the new length is not 8.5 anymore. You agree? Like, this is not 8.5 anymore. This is now 8.5 minus the squares. So would you agree with me, but the new length, let me zoom in here, the new length is going to be not 8.5, but actually 8.5 minus 2x. Okay? And again, if you look at this picture, the whole thing was 8.5, and I subtracted the 2 x's from it. If you understand that, you should know that the new width, and again, length and width in this type of rectangle, like they're interchangeable. If you understand that, do you understand that the new width is going to be 11 minus 2x? So let's write 11 minus 2x. The tricky part that most people understand is like, what about height? I don't understand height here. Well, let's take my paper, again, if some of you are visual learners, and I fold up, how high, how tall is this box, right? Would you agree it's as tall when I fold as x, right? When I cut an x out of it and I fold up, it ends up being the height of x. So on my height, I'll write x. Now, do you see how in step 2, what I did was make them all the same variable. For simplicity's sake, you're going to multiply this out, and to make this video a little bit faster, let me just multiply it out for you. You're going to get, when you multiply it out, you simplify it out, so you're going to get 4x to the third minus 39x squared plus 93.5x. Okay? So I figured out, first of all, what I was figuring out, first of all, what am I maximizing? And then I got it into one variable. Step 3 now, the one that you're comfortable with, or something that we've practiced a lot of, is now just do finding maximums and minimums. We found maximum and minimums just recently with a graph. Now let's try to find it algebraically. And you might have forgotten how to do this. Okay? If you remember, I take the derivative and I set it equal to 0, because the maximum and minimum always occurs either at the endpoints or where the derivative equals 0. So I'll take the derivative and set it equal to 0. 4x to the third is 12x squared. Minus 39x squared is 78x. And plus 93.5x, the derivative of that is just plus 93.5. And I set it equal to 0. Now, you have to solve this. It's a quadratic. You know, this is not very easily factorable. What I recommend you do is use a I use a quadratic formula app where you can go on Google where you can type in a different quadratic equation and it gives you what x can be. So I'm going to go to a different app. This one's called Quadratic Formula Solver. You see how it says A, B, and C? So what I'm going to do is I'm going to plug in A, B, and C based on the equation I have. A is going to be 12, B is negative 78, and C is 93.5. So let's put that in right now. For A, I'm going to put in 12. For B, I'm going to put in negative 78. And C is 93.5. Okay, and again, we'll go over this more when I'm with you guys. I type equals, and it tells me the real answers, or x is the same as 1.5, and I'm going to round this up, 1.59, and 4.92. So x is equal to either 1.59, I forgot the other one, 4.92. Okay, so far? So what I did, took the derivative, set it equal to 0, solved for x, and I got two numbers. Okay, one of these is the minimum and one of these is the maximum. Okay, so I don't know if you guys remember what to do, but once I have these numbers, what I'm going to do is I'm going to take them and put them back into my volume equation and see which one gives me the highest volume. So I'll take 1.59 and plug it in. I'll take 4.92 and plug it in. And again, to make this much quicker for you, I already solved it out. When I plug in 1.59, I end up getting, I'll do this in black, I end up getting 66. Okay, something around 66. When I plug in 4.92 into the equation, I end up getting negative 7. So what that tells me is to get the most maximum volume in this box, I should be cutting squares that are 1.59 inch sides. Okay, so the answer is, well, we could show you, but I'll just highlight it for you. Cut the squares at 1.59 inches and you will get a volume of 66 inches cubed. Okay? And that's how you solve those problems. Very, very high level thinking. The only way that you could really truly understand this is if you do a lot of practice problems. So I'm going to go over a few more of them with you right now in this video. If you turn the page, example number 2 says a farmer wants to enclose a rectangular area and divide it into 4 pens of equal size with fencing parallel to one side of the rectangle. What is the least amount of fencing he must use in order to enclose a total of 160 square meters? So a farmer, rectangular area, wants to put fencing around it and have 4 different pens for, like, say, 4 different animals. Step 1, in case you forgot, is always draw a picture. So here's my picture. He wants to enclose a rectangular area, and he wants 4 equal pens. So 1, 2, 3, and 4. Okay. And then what I'm going to do is I'm going to apply variables here. This is a rectangle, so what I'm going to do is I'm going to call this x and y. So one side of the rectangle is x, one side's y. And you may notice that this, where it says x, is kind of the same for all these pieces or this kind of fence. So I'll call all these x also. And some of you may be saying, like, how do you know that? Or like, whatever. I've just done so many of these that I get it. So I hope you get to the point where, like, we do so many of these, like, oh, okay, of course you do that. All right. The new step 1, if you remember, what I always tell you is, what are you trying to maximize or minimize? In this particular problem, I want to minimize, I want the least amount of fencing. Okay, I'm trying to minimize the least amount of fencing. So what I'm going to do is write the equation for how much fencing I'll need. Well, the amount of fencing I'm going to need is, if you notice, I'm going to need this much fence. I need an x, and x, and x, and x, and x. Do you agree I need 5 x's of fence? So fencing equals 5x. And then I'm going to need 2 of these y's, one on this side and one on this side. Okay. I'm trying to maximize that. If you remember step 2, what I need to do is I need to get this in one variable. I can't take the derivative of x and y. I need to figure out how to find the derivative with only one variable, and right now I have 2. So what can I do? Remember step 2, scan the problem for additional information, because any information they give you is probably to try to get it, they're trying to get it so that you can get it into one variable. So I noticed in this problem, the only piece of information they gave me, like number-wise, they said that they want to enclose 160 square meters, or the area has to be 160 square meters. So as my side calculation, would you agree that x times y has to be 160? Okay. So somehow I need to figure out how to solve this. Okay. It doesn't have to be like this. Another way you could have done this, not to confuse you, but another way someone could have thought of this is that, oh, maybe this is all like y's. So maybe this should be like 5x and 8y. Okay. You'll still get the same answer. So let's just say you did this. Okay. And let me change some of the problem just in case that you thought it was going to be like that. So let's change this. 5x plus 8y, right? And let's just say the new area, or the new piece of information that I got, I could write this down as, see how I have an xy, an xy, an xy, and another xy. Let's call that 4 xy's has to equal 160. So that's what we're trying to do. Now, again, I need to get this into one variable. So looking at this, I'm going to solve for x or y. It doesn't even matter which one you choose. We're going to solve for one of them. Let's just say I'm going to solve for x. So the first thing I'm going to do is I'll divide by 4. So xy equals 40. Or x equals 40 over y. So all I did was solve for one letter. Because now what I could do, if you notice, is if x equals 40y, now I could plug 40y into there. And I will only get one variable. So my new equation for step 2 is going to be 200. Oh, let me take one step back. 40 over y plus 8y. Okay, so far? And then when I multiply this out, I'm going to get 200 over y plus 8y. And these I can't combine. Okay? Now I have an equation that I want to find the minimum, and I have it in one variable. So step 3 is all we have to do is do the absolute maximum minimum process. Take the derivative, set it equal to 0, solve for that number, and plug it back into the original equation. So this one, you may say like, oh, I don't know how to take a derivative of 200 over y. Well, I could rewrite that. That means the exact same thing as 200 y to the negative 1, because y is in the denominator, plus 8y. Take the derivative of that, it's going to be negative 200 y to the negative 2 plus 8. So all I do is take the derivative, and I set that equal to 0. I will solve for y. Okay, so I'm going to subtract 8 from both sides. I'll divide both sides by negative 200, and I'm going to get 1 over 25. And again, I'm doing the calculations really quick. I'm just trying to get you to see what the answer is, but all this is algebraic. And some of you may not know this, but to get rid of that y to the negative 2 is, let me raise both sides. Here, I'll do it in red. I'll raise both sides to the negative half. Because if I do that, if I raise both sides to the negative half, negative 2 and negative half, these sort of cancel out. This just becomes now y to the 1. And if you put this, some of you may not know what this is, I put it into a calculator, I get y equals 5. And I don't even need to know, I don't even need to plug it in, but I already know that y equals 5. I know that if I need to get the most maximum, least amount of fencing for this particular pen, I know that these y's have to be 5 each. Okay. What about x? What does x have to be? Well, to get x, if you recall, I came up with a formula xy equals 40. So if y equals 5, that means x has to equal 8. So the question is, what is the least amount of fencing I need? Well, I could plug it back into my fencing equation, right? So I could plug 5 into here. 200 divided by 5 is 40, plus another 40. So the least amount of fencing I need is 80. And don't forget your units. So I only need 80 meters of fence, and I could enclose 160 square meters. So some of you might say like, "Oh, that's pretty interesting." Some of you like, "Man, this is so boring." But I mean, like, again, it's what I have to teach you. Okay. So let's just do one more, and there's a lot more I could teach you, but let's just get to 3 examples. Like I usually teach you 3 examples. Let's go to the next one. This one says cylindrical tin can. I want it to hold, think of another can or a bottle. I want it to hold 30 cubic centimeters. What should the circumference be? Circumference meaning this way. So I don't need as much tin to make a can. So I told you guys this before, like when you buy cans of beans or corn or tuna, that sort of thing. They always think about not like how it's shaped and how pretty it looks. Really, they're trying to make it so that they don't have to use so much metal to ship you their product. So it says a cylindrical can with an open top. Step 1, draw a picture. Here's my cylindrical can. And if you remember, it has an open top. Okay. Step 1 says, what are you trying to maximize or minimize? Now look at my problem. It says I'm trying to minimize the amount of tin needed. I don't want to use that much tin. Okay. So step 1, I'm going to write my equation, and I'll call it amount of tin. And that amount of tin, first of all, there's an open top, but there's also a bottom. So the amount of tin just for the bottom is going to be the area of a circle, pi r squared. The tin I need for this part right here, like this, like where the label goes, that amount of tin, if you don't know how to find this, it's actually circumference of a circle, okay, the circumference of a circle, times like the height of this can. So the amount of tin I need is the circumference times height. And now you guys are probably getting confused. Look, I got 3 variables, r, c, and h. Okay. So what I'm going to do is, in step 2, I need to figure out a way to get this in one variable. Okay. Well, the information that this problem gave me is that it's supposed to hold 30 cubic centimeters. So that tells me, the volume is 30 cubic centimeters. Okay. Volume of a cylinder, you may not know, pi r squared h, which is basically the area of a circle times h, has to equal 30. Okay, so far? And now what I'm going to do is I'm going to figure out a way to make this all in one variable. Now, this problem already has a pi r squared. So let's just replace, let's replace h. Okay. So what I'm going to do is divide both sides by pi r squared. H is the same thing as 30 over pi r squared. Okay. I still have the c though. Okay. C is circumference. You may not know this, and again, if you have this in the AP exam or for my exams, I give you these formulas. The circumference of a circle is the same thing as 2 pi r. So the cool thing about it is that I converted this into just an r, I converted this into just an r, so now I can change this, so now that it only has r's in the equation. So just to make this easy, I'm going to call this A equals pi r squared, which stays, plus C, and C in this particular case is going to be 2 pi r, and then H, which in this case is going to be 30 times, 30 over pi r squared. Okay, so let's plug this in. C now becomes 2 pi r, and H now becomes 30 over pi r squared. Now I only have one variable. They're all r's. And some of you may notice that this simplifies, so let's rewrite this. Pi r squared plus 2 times 30 is 60. My pi's, they actually cancel a pi on the bottom. And I notice that I have an r on the top and 2 on the bottom. So this whole thing just becomes 60 over r. Now, we can do the maximization part, but we'll save that for later. So that's all I wanted to teach you, or save that for later. What I'm trying to say is you're going to take this and take the derivative, set it equal to 0, and then find out where the maximum or minimum is. So that's how you solve these problems. For the rest of the class today, what I'll have you do is I'm going to give you a whole bunch of these sample problems. The math part, really, I'm not too concerned about. I think you guys can get the math part. All I want you to really do is, can you get number 1, this formula, and can you get number 2? Set it all into set it to one variable. So I'm going to put the assignment in your Dropbox. It's going to say like APPDER.5 problem set. Open up and explain everything. And again, I'll write this all down in Schoology. And what I want you to do is just do steps 1 and 2. Each sample problem I give you, write down what you minimize or maximize, and put it into one variable. And you'll record this video, and then you're gonna You're gonna do each one, steps 1 and 2. You're gonna record a video and post it to YouTube by the end of class. Some of you are gonna get stuck. Okay. If you get stuck, just stop the video like where you got stuck. Like do step 1 only, or just draw the picture or something. But I need to know where you got stuck on each of these problems. They're not easy, I'm telling you. So tomorrow in class, I'll practice a whole bunch of them. So thanks for watching, and I'll see you guys soon. Take care.